Today, we're going to explore electric potential, focusing on how work, energy, and voltage interact in electrostatics. Remember that work in physics happens when a force causes an object to move. Here, the force is pushing the block over a distance, and the amount of work done depends on both the size of the force and how far the object moves. If you push harder or move the object farther, more work is done. Moving an object against resistance means transferring energy, and this energy transfer is called work, which we measure in joules. Essentially, work is the product of the force applied and the distance the object is displaced. Here, we can see how the concept of lifting a mass against gravity parallels pushing a positive charge against an electric field. In the first image, a force is applied upward to lift a mass against the downward pull of gravity. Similarly, in the second image, an upward force is exerted to push a positive charge against the downward direction of the electric field. Both actions require mechanical work because they involve moving something against a force that naturally pulls it down. This analogy helps us understand that the physics behind these two situations are essentially the same, reinforcing the idea that forces in electric fields can be thought of similarly to gravitational forces. When we place two parallel plates with opposite charges, the space between them creates an electric field that is uniform everywhere. This means the field has the same strength and direction throughout this area. If we introduce a positive test charge, it feels a consistent force pushing it from the positive to the negative plate. This force can be calculated using the simple formula F equals E times Q, where E is the electric field and Q is the charge. Because the force remains constant at every point, moving through this field is like walking up a smooth and steady incline, without any sudden changes or bumps. This uniformity makes it easier to predict how charges behave within the field. Let's break down how work is done in a uniform electric field. We start with the basic formula for mechanical work, which is force multiplied by distance. Here, the force is the electrical force acting on a charged particle, so we substitute force with the product of the electric field strength and the charge. This gives us work as the electric field times the charge and the distance moved. This means the total work done depends directly on three key factors: the strength of the electric field, the distance the charge moves within the field, and the magnitude of the charge itself. Understanding this relationship helps us predict how much energy will be transferred when charges move through an electric field. When we push a charge through an electric field, the total work done depends on the size of that charge. However, the electric field itself, or the electrical landscape, remains the same regardless of the charge we move. This means that to better understand the field, we need a way to describe its steepness or strength that doesn't depend on the charge we're carrying. The diagram here shows a positive charge being pushed upward against the field lines, with work done equal to 10 joules. The distance moved, labeled d, and the uniform electric field, E. Here we see a positively charged particle, labeled plus 2c, being moved upward between two charged plates. The work done to move this charge against the electric field is 20 joules, as indicated by the arrow labeled W. Twice as much work is needed to lift twice the charge. Here, with a charge of 3 coulombs, to move this charge upward against the electric field by a distance d, work equal to 30 joules must be done. This work represents the energy required to move the charge against the electric force, illustrating the relationship between electric field, charge, distance, and work done in an electric force context. Now, let's look at how potential difference, or voltage, is calculated. It's the work done divided by the charge, so it tells us how much work is needed for each unit of charge moving through an electric field. This helps us understand the effort required no matter how much charge is moving. You can think of it like this. If the total work done is like the total fuel burned going uphill, then the voltage is like the steepness of the hill itself. This relationship helps us focus on the intensity of the energy needed per charge rather than just the total work done.
To understand what a volt really means, think of it as the amount of work needed to move a charge. Specifically, 1 volt represents the energy of 1 joule required to push 1 coulomb of positive charge across a point. This relationship helps us see voltage as a measure of how much effort is applied to move electrical charge, just like pushing an object with a force over a distance. Essentially, voltage normalizes the idea of effort to a standard way of describing electrical potential difference between 2 points.
Let's consider the idea of potential difference as if it were an electrical elevation on a landscape. Imagine you're looking at a hill. The potential difference, marked as V, is like the height of that hill. The electric field, labeled as E, represents how quickly the height changes as you move along the hill, or the slope steepness. If the slope is very steep, that means the field is strong, like a cliff you have to climb. If the slope is gentle, it means the field is weak, like a gradual incline that's easier to walk up. This analogy helps us understand the relationship between potential difference and electric field in a more visual and intuitive way. This image shows a positive charge at the center, with electric field lines radiating outward evenly in all directions. The field lines represent the direction a positive test charge would move, directly away from the central charge. You can see how the lines spread out, illustrating the radial nature of the field. The dashed circles highlight points at equal distances from the charge, showing that while the direction stays radial, the strength of the field changes with distance. The arrow pointing outward indicates the force experienced by a positive test charge placed in the field. This is a clear example of a radial electric field created by a point charge. On Earth, we use sea level as our zero elevation reference point, but in electrostatics, that 0 point is considered at infinity. This graph shows how the electric potential from a point charge decreases as the distance from the charge increases. While the field from the charge extends forever, it becomes weaker and weaker, approaching 0 the farther away you get. So, we define the absolute zero electric potential at an infinite distance from the charge, similar to how sea level serves as our baseline for elevation here on Earth. Let's look at the concept of absolute electric potential. This represents the work done per unit charge to move a positive test charge from infinity to a specific point in an electric field created by a charge, which we call Q. The symbol V stands for this potential, and mathematically it's expressed as the work, W, divided by the test charge, Q. So if we consider a point P at a distance r from the source charge Q, the absolute electric potential there tells us how much work is needed to bring that small positive charge all the way from an infinitely far position to point P within the field. This helps us understand the energy landscape created by electric charges in space. Let's take a moment to understand the key parts of this formula. Absolute potential, represented as V, tells us the voltage at a particular point. The constant K reflects how sharply the effects of the charge diminish over distance, often called Coulomb's constant. Q stands for the size or amount of the source charge, the factor creating the potential, while R is simply the distance from that charge, or the peak if you imagine it like climbing a mountain. All these elements work together to describe how the potential changes depending on the size of the charge and where you are relative to it. Here, we can see that the electric potential depends on the inverse of the distance, or 1 over r, while the electric field depends on the inverse square of the distance, 1 over r squared. This means the potential decreases more gradually as you move away, creating a smooth, curved slope. In contrast, the electric field drops off more quickly, which results in a steeper decline closer to the source. This difference helps explain why potential changes are more spread out compared to the more localized changes in the electric field. Let's take a closer look at how positive and negative source charges affect electric potential. A positive charge creates a peak or mountain of potential, meaning if you place a test charge there, it would require an external push to move it up that peak. This is because the potential energy is higher at the top, so the test charge doesn't move there on its own. On the other hand, a negative charge forms a well or valley of potential, causing a test charge placed nearby to naturally fall toward the bottom. As it moves down the well, the potential energy decreases and converts into kinetic energy, much like rolling down a hill. This helps us understand how charges influence the movement of other charges in the field based on the shape of the potential they create.
Moving forward, let's explore the concept of equipotentials in the context of electrical fields. Think of equipotential surfaces as contour lines on a topographic map, but instead of representing elevation in geography, they represent points of equal electrical potential. Each contour line indicates a specific voltage, so every point along that line shares the same electrical height. In this visualization, you can see how these lines form concentric circles around a positive charge, with the voltage values decreasing as you move further away. The three-dimensional shape helps illustrate this electrical landscape by showing a peak at the location of the charge, with the equipotential lines effectively creating slices at different voltage levels. This analogy helps us understand how electrical potential varies in space, and why no work is done when moving a charge along an equipotential line, since the potential is constant.
Let's examine how work is done when moving a charge in an electric field by comparing two paths. If you move a charge directly inward, or climb, from a potential of 100 volts down to 60 volts, it requires work, in this example 40 joules per coulomb. On the other hand, if you move the same charge along a path that follows the equipotential lines, like hiking around the ridge, there is no work done because the potential remains constant. The key idea here is that no work is done when moving a charge along an equipotential surface, since the electric field is always perpendicular to these surfaces. Work only occurs when moving between surfaces of different potentials, highlighting the relationship between electric potential and the electric field's direction. Let's take a closer look at the difference between electric fields in two common scenarios. In a uniform field, created by parallel plates, the electric field is constant everywhere between the plates. This means the field strength doesn't change with position, and it's calculated simply as the voltage divided by the distance between the plates. On the other hand, in a radial field generated by a point charge, the electric field is not uniform. Instead, it changes with distance, specifically varying inversely with the square of the distance from the charge. So, as you move further away from the charge, the field strength decreases rapidly, following a 1 over r squared relationship. Understanding these distinctions is key to analyzing how electric fields behave in different setups. Now that we've looked at the main characteristics of electric fields and potential in uniform and radial fields, it's important to understand the key differences. In a uniform field, like the one between parallel plates, the electric field is constant everywhere, and the potential changes linearly as you move between the plates. On the other hand, for a radial field, which comes from a point charge, the electric field decreases with the square of the distance from the charge, meaning it gets weaker rapidly as you move farther away. Similarly, the potential in a radial field changes inversely with the distance, so it drops off more gradually compared to the electric field. Keeping these distinctions in mind helps when analyzing different electrical environments and how charges and potentials behave. Let's take a closer look at the differences between a uniform electric field, like the one between parallel plates, and a radial electric field created by a point charge. In a uniform field, the electric field strength stays the same everywhere, which means it doesn't change as you move between the plates. The potential, or voltage, changes steadily as you move across the space, increasing or decreasing in a straight line with distance. The equipotential lines in this case are flat and parallel, spaced evenly, reflecting the consistent field. On the other hand, a radial field behaves quite differently. Here, the electric field strength decreases as you get farther from the point charge, following an inverse square law. The potential also drops, but it does so inversely with the distance, meaning it decreases more gradually as you move outward. The equipotential lines aren't flat, but form concentric spheres around the charge, spacing out wider as you go further away. These differences help us understand how electric fields and potentials behave in different physical setups, guiding us in both practical applications and theoretical analysis. If you found this material helpful, you might want to check out physicsib.com. It offers a structured, interactive course that can guide you through the topics step by step, helping you build a solid understanding in a clear and organized way.
If you found this presentation helpful, please consider liking and subscribing to stay updated with more content. For a more structured and interactive learning experience, you can visit physicsib.com, where you'll find courses designed to support your studies effectively. Thanks for watching, and I hope to see you there.